Hello, this is Usman Messerwala from Team 1067 of College of the Canyons with our presentation on Problem B, time to throw the bike. So, we were asked a few questions, which were, when should a rider stop pedaling and shift her weight backwards to thrust the bike forward? What is the best position for the cyclist, and what are the trade-offs for a more precarious hand position? What is the time interval that a professional cyclist must exploit? And finally, what is the maximum amount of time that can be made up? We can actually go ahead and answer the second question right away. Since a bike throw essentially consists of a rider pulling their torso back, thereby shifting their center of gravity and slowing themselves down very slightly, the conservation of momentum shows that when the bike's handlebars are pushed, the bike will speed up to a tiny degree. The biker in the green has a great position as he is sticking his torso back as far as possible, but if he were to place his palms on the handles instead of fully gripping them, he may have been able to gain more speed on the front wheel, although losing control in the process. We have quite a few variables that we've defined based on averages and certain weather conditions. For example, this rho, or the air density, we gave 1.23 kilograms, which is only the air density at 15 degrees Celsius. Here are some assumptions we made. We assumed that the friction between bike parts, such as the pedals and the tires, is negligible. We assume that kinetic friction does not act until the rider has stopped pedaling for the throw. We assume that drag keeps the velocity consistent until the moment of the throw. The bike is on flat terrain, and that the bike throw happens instantaneously. So here is our setup, where x is the distance from the finish line. We also said that x is the point where the bike is thrown, and the time is based on however long it takes to traverse that x. Comparing this x distance, or the time it takes for a throw and non-throw, was the basis of our model. The first equation we use is related to the conservation of momentum, where the velocity only changes as a result of the throw and becomes 12.1 for the very moment after the throw. For the non-throw, we used a consistent velocity, which was this 12 meters per second. To start finding our differential equation, we started by factoring in drag, that, as previously mentioned, only acts after the throw. The drag equation is shown right here. So next we factored in friction, since its rolling friction is found. Next we factored in friction, and since that's only rolling friction, we found it by multiplying a rolling resistant constant mu by the normal force, or mg. Plugging these forces into Newton's law, or Newton's second law, gives us an equation such as this one, where the forces are negative as they act against the bike. Then, we subbed in x prime of t for velocity and x double prime of t for acceleration in the aforementioned equation, where x represents the distance and t represents the time to traverse it. We used a Python script written with symbolic math library SymP to display our equation, which is shown here. It's been rearranged a bit and set equal to 0. As you can see, this x double prime of t is the acceleration, and this is the velocity. To solve the differential equation, we use the midpoint method. Here is an illustration of the method, right here. And here is a formula, a generic formula for the method as well. We created this method also in Python, which the code is shown right here. The function RK2 represents the midpoint method, which was that equation I showed, or the formula I showed a little bit earlier. And we called it RK2 because the midpoint method is also known as the Runge-Kutta second order. The function throw has our variables that we chose, with the average values attached, and is creating a function x of t. The non-throw function right here is just the formula distance equals velocity times time, where the velocity is 12 because we assume that the forces of friction and drag kept it constant without a throw. The code at the bottom here is how we graphed our differential equation, representing the throw versus the non-throw. And it's very obvious right here with this graph that they're extremely close. The throw is in blue and the non-throw is an orange dash line. It's extremely close. This is what we expected because we know that the bike throw only provides a very small benefit, but that benefit can make a difference in a race. So here's an updated graph showing the point where they intersect, which is also the point that it becomes less beneficial to throw at than not to throw at. And the intersection is right here. Back to the slides now, we can address the questions. So the answer to the question, when should a rider stop pedaling and shift her weight backwards to thrust the bike forward? Well, that's anywhere from 5.9099 meters or less from the finish line, which we saw was the intersection point. The time it takes to traverse anywhere from about 0 to 5.9099 meters is faster if there is a throw at that point than not. The next question is, what is the time interval that a professional cyclist must exploit for this move to be effective? And that interval is almost half a second. We found this by taking the intersection point and plugging it into the d equals vt formula. As you can see, there is only an extremely tiny window that the rider can take advantage of a throw in. So they would have to be prepared to take advantage of that 0.5 second window. The final question, which is what is the maximum amount of time that can be made up, we could not exactly answer, but we did find the maximum amount of distance, which is extremely small. Only about a tenth of a meter can be made up in the conditions we modeled. Speaking of conditions, we had many of them. For example, the weather or the rolling resistance. For the first limitation, our model cannot account for anything other than flat terrain. We would have had to include additional factors into our differential equations that could have changed it quite a bit based on if the terrain was up or down. Other limitations, which were most likely at the end of a race, a rider would probably have a positive acceleration as they're trying to go toward the finish line as fast as possible. Our model only works if the acceleration before a throw is 0. In the equation that stems from conservation of momentum, masses may overlap, such as the rider's hands and the handlebars. We have chose to keep it separate for simplicity. So the 70 kilograms that I mentioned earlier, or that I showed earlier, is the rider's mass, and the 7 kilograms is the bike's mass. Likewise, the velocity of a rider is talking about the rider as a whole, and not accounting for the fact that the velocity of a rider's torso compared to their forearms may differ. The velocity of a rider's torso may be slightly tinier than their forearms. Here are the references we use to find some of the constant and variable values. Finally, a big thank you to our coach, Ms. Kovacev, for taking so much time to prepare us for the competition.